Welcome once again to the UNU-INWEH public event, the Science Talk. I am your host, Professor Grace Oluwasoya. Before presenting the distinguished speaker for this morning, I know you are joining us from all over the world, so it may be, the evening or afternoon where you are joining us from, but here in Canada, it is 10 a.m. I welcome you, especially those joining us for the very first time. Please note that there will be an interactive Q&A session at the end of the presentation. At that point, we will take, your comments or your questions or any other contributions that you may have. Please type your questions or comments in the Q&A chat box. We will pick them from there at the end of the presentation. Thank you. The topic for today's talk is a novel approach for soil degradation using big data and AI for soil health management. So let's talk. Our distinguished speaker for today is none other than Professor Nima Shokri. I hope I got the pronunciation well. It will tell us about that, in a few seconds. Professor Nima is a professor of geoinformatics at the United Nations University Hub for Engineering for Climate Change at Hamburg University of Technology in Germany. His research is dedicated to tackling global challenges on water, soil, and environment. He is passionate about creating new knowledge through research and innovation, especially in developing innovative measurement tools and predictive capabilities that harness the strengths of sensing technologies and big data analysis. I know people like big data, especially in this period. He has integrated theoretical frameworks with state-of-the-art modeling and experimental techniques, leveraging cutting-edge tools like AI, computational fluid dynamics, environmental sensing technologies, thermal imaging, just to mention a few, to offer new insights and perspectives on the complex interactions between soil, water, and the atmosphere. Together with his team at Hamburg University of Technology, they have provided accurate and quantitative insights into multi-scale and multi-phase ecohydrological processes occurring near the Earth's surface, from which you'll be hearing a bit more today. So without further ado, please join me in welcoming Professor Nima Shokri. Welcome, Nima.
Thank you, Grace. Hello, Grace. Do you hear me?
Yes, loud and clear.
Fantastic, fantastic. Thank you for the great introduction. I'm Nima Shokri. You pronounced the name perfectly. And it's an absolute pleasure today to have an opportunity to talk about one of the active projects in our institutes on soil degradation. And so let's begin. I like to start my presentation, my talk about saying a few words about the importance of the soil. I really can't overstate the importance of the soil for the planet, for the human, and it breaks my heart to remember that how few we actually think about soil. As we speak, the soil is doing the job for us. They're providing the services that it is supposed to provide. And I just feel that sometimes we don't appreciate it enough. When we say soil, obviously immediately everybody or most of us think about food security for good reason. Soil healthy soil is essential for food security, and that provides basically food to nourish our children who are driving the civilization, that will feed billions of people, but beyond food security, soil contribute to biodiversity, to water regulation, to climate regulation, to social welfare, And because when the soil is degraded and the soil is not healthy, that will affect the crop production, that will affect the lives of farmers, and they can't operate their business anymore. And we all know what are the adverse consequences of the socio-economic consequence of the unemployment. So this is the illustration from FAO, that basically they list a couple of the functions that soil contributes to. Let's say when you talk about carbon sequestration, when you talk about cultural heritage, when you talk about nutrient cycling, climate regulation, flood regulation, biodiversity, in all of these topics, somehow you're dealing with soil, healthy soil, and soil is at the top of the agenda. And this is as well not new. I mean, humans basically know that since thousands of years, since ancient times. When you look at the historical fact, you will see that, for example, in the past, a couple of thousand years ago, the Sumerian civilization essentially collapsed because of the soil degradation they had. So they were in Mesopotamia, the nowadays Middle East, basically part of the Middle East, and the soil quality that got that bad that they couldn't cultivate there anymore. And interestingly, at more or less same time, in those times, the Egyptians, they actually figured out how to manage their soils, because the Nile was there, and the water irrigation system, and so on and so forth. And apart from this historical fact, when you look at the old books, religious books, the books that are thousands of years they have been around, and you're impressed when to find that so many times they refer to soil, so many times they highlight the importance of the soil. And this is an example, for example, from Leviticus, which is the third book of from Old Testament, the verse 25. It says that, I like actually to read that one, that when you enter the land, this is the Lord talking to Moses, when you enter the land, I'm going to give you, the land itself must observe a Sabbath. Sabbath is like rest, like sabbatical. The land itself must observe a Sabbath to the Lord. So basically, it's a right for the land. It's not only the soil has duty for us to provide food, but it has a right. It has the right to Sabbath. And then the question is, how do you basically rest soil? And the solution, the suggestion here is that for 6 years, sow your fields, and for 6 years, prune your vineyard and gather the crops. But in the 7th year, so for 6 years you do the job, but for the 7th year, the land is to have a year of Sabbath rest, a Sabbath to the Lord. Don't sow your fields or prune your vineyard. Okay? And I mean, if this is not about conservation of soil, if it is not about preserving soil, then what is it about? And it's not only restricted, constrained to Old Testament. You can find similar statements, interaction in Quran, or for example in Buddhism, especially in Buddhism. When you look at all this interaction they have between human and nature, you are surprised to see how many times the references goes to the soil. So this is an interesting example, the story of the Bodhisattva, which is a central figure in Buddhism, is a farmer. And when you go through this story, when you read this story, that and you will see so many references to the idea of soil protection and the importance of the soil. And what I learned actually from that is interestingly, when you read this old text, you never, or at least I never get the feeling get the idea of exploiting the soil. It's all about nurturing soil. It's all about resharing the soil, preservation for the future generation, and so on. And it is not surprising because the ancient civilizations, they found that they actually figured out that their very existence heavily depend on the fertility of the land for survival. Okay, and we don't need as well to go to 2,000 years ago. Another example is the Soil Conservation Act enacted in 1935 by the Senate and House of the Representatives of the United States. And this is, to me, is the first like a first written document in modern history that acknowledges the soil conservation, soil preservation, and so on. Here you see President Franklin Roosevelt, where he was signing this legislation aiming at combating soil erosion and preserving natural resources in 1935, where he said these famous sentences that the nation that destroys its soils destroys itself. Okay, so we have a long story of appreciation and acknowledging the importance of the soil throughout the history, throughout different religions, in modern history. However, after almost 90 years of this Soil Conservation Act of 1935, there is no well-defined mathematically and physically driven approaches to quantify soil degradation. Okay, so when you talk to soil scientists, when you talk to climate scientists, to engineers, of course, everybody talk about soil degradation, but if you ask them, what do you mean by soil degradation? You know, how can I quantify that? How can I predict that? How can I quantify what's the effect of temperature? What's the effect of land management? What's the effect of the vegetation? Mathematically, how can I do that? There is no answer. There is no well-defined procedure that you follow, and then you get, okay, this is the soil degradation. And then you can compare this with another time throughout the history, with another location in the world. So there is no well-defined well-defined approach. And you can say, you know, take it easy, why it is important. So there are so many things that we don't know how to calculate. Why we should develop a well-defined methodology to calculate soil degradation? And the answer is because soil degradation matters. It threatens, soil degradation threatens security on multiple fronts. And it's not only the food security, it's a matter of national security. Because as I already explained, when the soil degradation happens, when the soil collapse, a lot of socio-economic activities will be impacted by that, and people lose their job, and that will come with its own consequences. There are cases in Middle East, for example, because of the combination of the mismanagement and the climate change and a lot of other things, this farmer basically lost their land. They cannot cultivate anymore, and some of those people in the end ended up radicalizing. So the topic is really much bigger than just the soil itself, but the consequences that we may face if we don't pay the attention the soil deserves to receive. Okay, so these are a couple of numbers. This is from the United Nations Environmental Program 2017 fact sheet. That is, their estimate is that 1/3 of the Earth's land surface is degraded, 1/3, and affecting about 2.5 billion people worldwide. There is a very good report by European Commission, came out in December, I believe, December 2022. But they estimate that 60 to 70% of the EU soils are unhealthy. Okay. And unhealthy soils, as we know, lead to food shortages, price hikes, exacerbate climate change, because soil as well plays a big role in regulating the climate in terms of the evaporation as being part of the water cycle, runoff, infiltration, right? Social instability and more. Okay, and there is this, it's again, the estimate is from the UNEP that about $10 trillion, I don't even understand what does $10 trillion mean. I probably understand $5 billion, maybe $10 billion, but more than that, I don't even know what does $10 trillion, I don't have imagination for that. $10 trillion every year cost in lost ecosystem services because of the land degradation. Okay, and obviously that aspect motivated. There is a rising interest in recent years on quantification of soil degradation. Put numbers, not qualitative explanation. Qualitative explanation, they have enough of that. But mathematically, physically driven calculation that shows me that this land is degraded, this is the intensity of the degradation, and that's how it evolves over the past 20 years, over the past 50 years, or that is what's going to happen to the soil over the next 50 years. Okay, so there has been a lot of efforts recently, and they provide valuable information. They provide very valuable information. They help us to understand the processes, the mechanisms affecting soil degradation, I'm going to show you a couple of them today. They're quite recent ones. You see here, this is 2024, published a few weeks ago in Nature Communication. This is as well from EU Soil Observatory. That is Panagos et al. That is our colleague, 2024 again. And this is another one in 2021. So these are really the recent studies, and I'm going to explain for you what is the shortcoming of this calculation. And so what they do here, let's just look at the middle one, the map in the middle. So what they do, they first determine some indicators, some process that indicate the soil is degraded. Okay, and in this case, the paper 2021, they have five indicators. They say soil erosion, aridity, vegetation decline, salinization, and soil or organic carbon. We consider it as the indicators of the degradation. Okay, and then what they do, they determine a threshold, and that threshold comes from expert opinion, experiences from farmer, literature, some empirical studies. But to me, they're rather, rather subjective. For example, we say soil erosion. If it is less than 2 tons per hectare, that is okay. If it is more than 2 tons per hectare, it is not okay. So if it is okay, you give 0. If it is not okay, you give 1. You do the same with aridity. You do the same with vegetation. You do the same with salinization. For example, if the salinity is less than, I don't know, let's say 2 decisiemens per meter, we say it's okay. When it is more than 2 decisiemens per meter, it is not okay. That number will be 1. Okay? So, and then for every pixel that they have, they add them up. And that's why the range here changes from 0 to 5. Why? Because there are 5 indicators from 0 to 5, right? 0 means 1 basically means 5 means there are so many factors basically affecting the degradation, and 0 means there is no or 1 thread or there is no thread. Okay, the same story is here. That is another study from EU Soil Observatory, exactly the same method. However, they have more parameters. They have erosion, pollution, nutrient, biodiversity, etc., etc. They go through the same story. They have threshold for every mechanism, and then you add them up, and your mark changes from 0 to 9. And this is another story that is here again. You have more parameters, more indicators of the degradation, and you get this map. But the shortcoming of this, although they provide useful information, but the shortcoming is that the red color here in this middle figure, the red color does not, in my opinion at least, the red color does not necessarily mean the soil is worse than the green color, because all it means is that the number of the threat to soil degradation is more than the green area. But imagine if only soil erosion is a problem, but in a very severe condition. Let's say you lose 30 tons of soil per year per hectare. Okay, so 30 tons of soil, right? And so that soil essentially is very, very difficult to cultivate. But if it is the only threat, you get number 0 or number 1, right? But in the case of red one, you could actually have all this threat, but right at the threshold, just the 2 tons or 2.5 tons per hectare or per year, and then you will have like 2.5 decisiemens per meter and so on. You add them up, the number will be 5. The color is red, but it doesn't tell you about the intensity of the problem. Okay, about the intensity of the problem. That's one issue, and also it is as well difficult to talk about the dynamics of the changes. Okay, so that was the motivation of our work. That we come up we team up basically with some of the teams that developed these studies to come up with a new approach, with a novel approach that quantify the intensity of the degradation. Okay. And so we considered 4 soil health indicators, and that these 4 little things I put here, soil erosion, EC, pH, SOC, that is a work of about like 6 months, if not more, that we choose these 4 parameters. So basically, soil degradation, there are chemical degradation, there is biological degradation, there is physical degradation, and all of this type of degradation is covered by these 4 indicators we listed here. But I leave the door open that maybe in future people can add more indicators. But for us, We work with these four. And also, degradation is a very broad term, and I hesitated to use degradation here. I use vulnerability, soil vulnerability index, which I actually don't like the name that much. We are still, yeah, but for now, let's leave with soil vulnerability index, SVI. So how it works is that we scale the values of the soil erosion we have across, let's say, Europe, the values of the EC we have across Europe, the value of the pH, the value of the SOC, we scale them between 0 and 1, okay? We add them up and then take an average, and that will give me one number that varies between 0 to 1. 1 means things are very bad, 0 means essentially Merry Christmas. Everything is fine, and we're okay with the soil. Okay, so that's the idea of this index. And so we have, for those of you who may not know about Lucas, in Europe, we have a very big campaign running since like 2009, I believe. It's Lucas, just Google Lucas. What they do, they go to about 20,000 spots. You see here, this is like close to 20,000 spots. They did it in 2009, 2015, 2018, and they did it recently, so the new data as well will come out. So they go to 2,000, sorry, I mentioned 2,000, it's wrong, 20,000. They go to 20,000 spots. It's a lot of work. It's actually, I believe it's a couple of €100 million project running. They go to 20,000 spots. They get the sample and they analyze soil for a variety of properties, EC, I don't know, SOC, pH, vegetation, the soil physical properties, porosity, densities, a lot of data. And that is open access. So everybody can go and basically use the data in their analysis. And in fact, in the 8 program, the UNU-8 program, so for in the soil health module of the UNU-8 program, we have we added a link to Lucas. So for those who are interested, you can easily find the data. And the blue dot here shows the location of the measurement. So we have the data of these 4 parameters I am interested, soil erosion, EC, pH, SOC, on these 20,000 roughly a spot across Europe, okay? So therefore, I can just take these values, put it in this my equation, and then I calculate my SVI, soil vulnerability index. So and that's the result you get. On the left side, this one is our calculation. The color map changes from 0 to 1. 1 is bad, like degraded soil, and 0 means, as I said, like Merry Christmas, everything is fine. And then, but the beauty here is that the numbers here that has meaning basically. That gives you the intensity of the degradation. And in terms of the comparing, so we compared that with this map that the EU Soil Observatory released in 2024, but their method is completely different. The numbers changes from 0 to 9. And 9 means 9 different factors is affecting. 0 means like, 1 means like 1 factor is threatening the soil. The number doesn't say anything about the intensity of the degradation. And so when you compare the data here, qualitatively, you see that we get the Spain when we have the red and the soil is not good, and then they have as well in a kind of reddish area in Spain, Italy as well, the Italy, and like north of the France, this part of the France as well. You see, so the area that are red on the map on the right side, we more or less have the same red area and green area on the left side. And then I'm going to show you a little bit. We wanted to spend a little bit more time with this new index, soil vulnerability index. What does it mean? Like the vulnerability index of 0.2 or 0.8, 1. What does it mean exactly? So here we have this super smart postdoc in our institute. Mehdi, he basically looked into some of the spots. Let's say this is in Poland in 2015. In 2015, so you have the SVI, you can calculate now for 2015, you can calculate it for 2017, and then you can see where in Europe the situation got worse or got better. So, for example, you can see in Poland in 2017, the SVI was 0.41, and in 2018, it is 0.87. So it's a massive increase from 0.4 to 0.8. in like only 3 years. And so Mehdi goes to the Google imagery to see what's going on in that area. And then you see that this is 2015. And in 2018, you see there is a highway. They built up a highway in that spot. And that was really, I was very pleased to see that the index can capture changes at this scale. And we had as well other cases. For example, there are cases where the SVI is very high, that is, let's say 0.72. 3 years later in France, we see the SVI got better. That means the situation got better. And you go to the satellite image of that spot, and then you see that in 2018, you see that some forestry is going on here, and some management, land management is actually happening here, and that is possibly one of the reasons the SVI is getting better. Or for example, there are just more examples. For example, cropland. When you say SVI 0.2 in cropland, you can expect a figure like that, an image like that from satellite. But in cropland, if the SVI is, I don't know, 0.94, that means very, very bad. Close to 1 it is closer to 1, the worse it is. You see the photo is like that. The same goes for grassland, 0.22, but 0.85, you see the situation is like that. Or I have problem here. Yeah, or here you see this is forest. This is a very good SVI, 0.16, right? But then another area in forest that is 0.8, and you see the difference in the land situation. At least visually, we can see meaningful changes in the images. So this is the SVI we have. So the title of my talk was about a novel approach to quantify degradation. So that we already delivered. That's the approach. But then I say using big data and AI. So where does the AI come to play a role? So I have now a tool, a quantitative tool that allows me to calculate the intensity of degradation at different times depending on the data I have. Okay, so in the next step, what we did, we used AI algorithms. We used AI algorithms to develop models capable of predicting degradation on the different scenarios. Okay, and how it works, this schematic basically perhaps provides much better than what I talked, but that's so now I have this SVI. That's the map of the SVI I have. In the AI terminology, let's call it, this is the target parameter, because that is my target parameter. I want to predict that. So I have this one, and then I get a lot of other data, the drivers for degradation. What are the drivers for degradation? Why the degradation happen? You just name it. Could it be because of elevation of the land? Could it be because of temperature? Could it be because of evaporation, nitrogen, phosphorus, potassium, land cover? You can list the parameters that you think they are the ones that are deriving the degradation. Okay, and of course there should be some physics, some chemistry, some biology behind that. So this is why we call it. It's like a physics informed that the system we design. It's not like a black box. We really choose the parameters that, according to the literature, textbook, expert opinion, these are the drivers. Anyway, so we have a lot of data from satellite remote sensing. We have a lot of data from other databases that are not necessarily satellite remote sensing. So these are the drivers. And then I have the target parameter. Then put everything in one matrix, right? I mean, I'm simplifying everything, but that's the idea. So this is the target parameter. That's the time. And that's, let's call it predictors, right? The one that predicts basically the behavior of the target parameter. You can call it covariate, for example, so that you have this P1, it should be P2 actually here, P1, P2 up to Pn. And so I have this massive matrix, and then I expose this matrix to an AI algorithm. To an AI algorithm, you can choose like different algorithms here. I don't know how to do that. Mehdi does that. And I'm just a privileged working with the smart people. So we expose this data to the AI algorithm, and then we do model training. We do them parameters tuning, right? and then we get the outcome, we validate that, we evaluate the performance of the prediction compared to what we have. So here you see one of these examples. So this is our prediction. This is the observation of the SVI, which is this map. So I have the SVI, and then I predict that, and this is the comparison. And then, yeah, when I'm satisfied with the model, then I can predict the SVI across Europe. Okay, so now, so remember, this SVI, it's a discrete point. So I have there is this couple of €100 million funding going on. We go to the Lucas, we get the data, and then we calculate the SVI. But now with this tool, so we calculate the SVI only at those 20,000 points. But now I have the continuous. I have to keep an eye on the time. Yes, actually, I certainly should. So then we can predict the SVI continuously across Europe. Okay, and then this is the result that we have. So this we submitted this paper, I believe, like last Friday. That here you see the prediction of our SVI in 2015. This is in 2023. This is the difference between these two guys, that you can see where in Europe things are getting worse, where things are getting better, and that will help to devise the necessity action plan to save the soil. Okay. Not only that, but we can as well get a lot of other information. For example, we can study the relative importance of different drivers in degradation. So this is, I don't know, precipitation, temperature, land surface temperature, the kind of vegetation, kind of the land management. So we can really see how different parameters affect the degradation. Okay, I think I have a few more minutes time, so I'm going to skip the next slide. But you can ask questions about me later on about it, that where we see the effect of every single driver on the SVI. So now we have a tool to predict the degradation across Europe. But our next step here is that, so what we wanted to do is that, so remember, how do you say a soil is degraded? So we determined 4 parameters. We said EC, pH, the SOC, and erosion. Okay, so we wanted to delve into each of these indicators. So one of them is EC. EC is electrical conductivity, which is a measure of the soil salinization. Which refers to the excess accumulation of salt in the environment. When there's too much salt, it harms the environment, and it has a lot of serious consequences on ecosystem, on socio-economic activities like economic welfare, human health, deruralization, stability of the communities, and so on, and also on crop production. So we basically utilize. There is actually a little video here. I want to play that. Why not? So here there's 2 soil samples, one is salty water, the other one is a pure water. So add the salty water and pure water to soil, and then we plant here, and you see what happens. So the right one is with salt. The one without salt, you see the plant is happily growing, everybody is good, is happy there. But with the salt, you don't see any plant growing. So just addition of a little bit of salt was enough for this magical medium that has been around for thousands of years. It completely loses its performance. So that's why it's important to understand the salinization and soil salinity. And so what we did, the methodology is the same as the degradation story, that we have data on a global scale where salt measured, concentration of the salt was measured. Okay, and then here, this is the early work that we did. I think it was 2020, but we listed a lot of basically driver for this salinization. So here you see more than 40 different parameters. We list that these parameters are the one affecting the salinity. Okay, and then so I have the salinity measurement For every measurement, I go and find these 40 parameters, okay? And then I make a massive matrix of data. So here I have about 200,000 data points. So 200,000 data points I have on this side, 43 on that side. So you're looking at like close to 10 million data points, and I expose that to AI algorithm, and then I train a model relating the salinity to these drivers. In terms of the evaluation of the model, this is our predicted values, and this is the observed values, okay? This one, okay? And here I have 40,000 data point. In here I have like 200,000 data point, and the R-square is 70%. You can say no, it may not be that good or it's okay, but we need to put things in context. The other product that was available before this study, which is heavily used by almost many, all major reports from UN, from other places, is the data provided by HWSD, Harmonized World Soil Database. And this is prediction versus the observed. The yellowish color, the orangish color is our prediction, the way ours work, and the dark brown is the HWSD. And the same goes for here. So ours is not perfect, but I believe this is performing better. So now this is the validation of the model. Then I have the model. I can use it to predict the salinity on a global scale. Okay, I can predict the salinity on a global scale with a very high resolution that I can go to the border between Utah, California, Arizona, see exactly how salinity is changing. Not only that, but also I can go through time as well. And that is the first data set in the world that really provide the global map of salinity from 1980. I believe this is until 2018. Yeah, so we can go on a global scale and see how the salinity is evolving. Then not only that, but also you can now talk about future climate, because if your drivers, let's say temperature is one of your drivers, let's say evaporation is one of your drivers, let's say precipitation is one of your drivers, we have future predictions for these values. We have future prediction for these values from the climate model. So what I can do, I can use those future prediction to train models to predict the future of the salinity. Okay, this is the validation of the model. I'm going to skip that for the sake of time, but this is the final result that you see here. This is the global salinity under different climate scenarios. That is RCP. This is from CMIP 5, the case 4.5, 8.5, or CMIP 6 here, 245, 585. So I can, depending on different climate scenarios, I can predict what will be the salinity in the future. Okay. So I have one more slide, kind of scientific slide. Should I skip that, or do I have time to continue this?
Please continue.
Okay, so this is very close to my heart, so I'd like to say a few words about that. So this is a very interesting figure. This is how can I explain that? So to make our future prediction, we use 16 different climate model, but I believe it was like 29 different output of the climate model. Okay, we use, let's say, 16 different climate model. And then for every climate model, we predict the salinity. Okay? So here, the closer to blue color means no matter which climate model I use, the predicted trend stayed the same, not the predicted value. I didn't go that far, just trend. So let's say one model says the salinity goes up, the other one goes down. Blue means no matter what climate scenario you use, we are predicting the same. And yellow means depending on the climate model you use, you get different value. And that is a very, very important figure in terms of the communicating our results with end users, with policymakers, because I hear that sometimes all the blame is on politicians, that why they don't do anything, why don't you do that, why don't you do this, to do that. I agree, sometimes the wrong decisions are made, but sometimes as well, we as the scientists, we need to work harder to provide more reliable models and data so that they can rely their decision on that. So imagine in California, some areas is yellow. What does yellow mean? Yellow mean, if I use, for example, the model from Hamburg, the climate model from Hamburg, the data says the salinity will be worse. And if I use the model from Japan, it may say the salinity goes down. And then how can I develop a reliable policy that I can sell to the farmer? Because the decision you make, that affects the lives of farmer, that affects the job, that affects the GDP, a lot of other things. I don't want to spend more time on that. So that necessitates the need for more reliable data and accurate representation of the whole picture. And then you can, of course, say, why should we do that? I mean, why? And this is basically concluding here. You can say that, so you went through all these 40 minutes of talk. I mean, why? It's just soil. And the answer to that is, I noticed that I'm giving the talk to the United Nations University. I thought, why not to bring the reference from the SDGs, that if you want to achieve SDGs, it's a necessity to have a healthy soil. Without healthy soil, you have to say ciao to SDGs. To my surprise, there's no SDG focused on soil. That is actually very interesting to know. But you can it's difficult to come up with SDG, but it does not interact directly with the healthy soil. And as we know, the world is falling behind on achieving the SDGs. So my proposal is, why not to invest in soil health? You know, it will bring soil back to life. It will regulate climate. We all like climate, so it will regulate climate. It will maintain biodiversity. It will support food security and many more things. And above all, it creates job. Okay, and I believe the formation of the UNU hub on engineering to face climate change at Hamburg University of Technology is a step forward to achieve the goals that we have related to the soil health. We have two clusters. One of the clusters is focused on global soil health, water and climate. And you see here the photo of the inauguration event, and with all the esteemed guests we have here. And I believe we are in a very, very interesting time to live, to come up with novel approaches to develop reliable methods to enhance soil health and conservation. And my take-home message is that soils are fragile. It can take thousands of years to form, but can be destroyed in an hour. In hours, there is an oil spill. The soil that came to us 1,000 years ago, it can be destroyed. So #save soil. And I can't finish my talk without contributing without acknowledging my colleagues, Panos Panagos, who is from the Joint Research Center of the European Commission, Danny Orr from the University of Nevada, Reno, David Robinson from the UK Center for Ecology and Hydrology, Professor Adis Azapagic, she's from University of Manchester, Pasquale Burelli, that is from the Roma Terra University and University of Basel, and Milad Aminzadeh, senior scientist at Hamburg University of Technology. Amir Hussein Hassani, he's from Nilu, Norway. He was my former PhD student. He's a senior scientist in Norway now. And Mehdi Afshar, who is our postdoc at the Hamburg University of Technology. You see Amir and Mehdi are highlighted by the red box, indicating the job, the majority, if not all, of the credit should go to them. I just here present their work. Thank you very much for your attention. Thank you.
Thank you, Professor Nima. I really appreciate the passion with which you have told us, save the world. So this is go save soil, and we did on that. But with soil also is water. But I know you're pitching in from the angle of water, I mean for soil, so that's so fine. But we'll start on a lighter note. Initially, I wanted to pick on you that until you show me the SBI from Nigeria, I won't believe anything you say. But later, I realized that, okay, we've gone beyond, showcasing this in Europe, and we've seen, some data across the globe. But you ended by saying something about reliable data. I need you to clarify that. What do you actually mean by reliable data? Are you referring to primary data or reliable secondary data? Let's start from there. One.
Yeah, that's a very good question. I told you this slide is very close to my heart because it conveys a much bigger message than it shows here. So look, when we do this type of predictions, we feed the model with wide range of data. So in this case, some of the input of the model is the climate data. Okay. And then I use the climate data, and there are different climate models. We could, of course, work with only one model, but we didn't want to do that because the climate model, they sometimes their predictions quite different. So what we did, we basically use all the models that are available to us and use them to predict our soil salinization. But what we see here, depending on the model I pick, look at this yellow area. The yellow area. What does yellow mean here? Yellow means depending on which model I get, my model says, depending on which climate data I use, my model says the salinity may go up or may go down. So I can't make, as a policymaker or as a farmer who want to actually to devise the strategy to manage my land. So I don't know which climate data I should use, which model output I should use. Is it reliable? Because with one model you say it goes up, with other one goes down. So you ask, what do I mean by more reliable? What do I mean is that we need to find ways. I mean, in this particular case, this is more referring to the climate scientists. They need to find ways to produce more reliable, possibly with higher resolution data. Remember, majority of the data that is used in IPCC report, the pixel they have on a global scale is like, I don't know, 30 by 30 kilometer, or sometimes 100 by 100 kilometer. So for the 100 kilometer by 100 kilometer, there is one climate point, well, one point that gives you temperature or this. And so could that be a possibility to do this type of simulation at much finer resolution? Obviously, the challenge there is the computational capacity. And I know there are some major global effort actually to achieve this. For example, there is this initiative, very big initiative in Hamburg from Max Planck Institute for Meteorology. They are very big in climate. They call it EVE. They call it EVE. In fact, the director of the UNU-INWEH, Kaveh Madani, was a part of this initiative they started in Hamburg called Climate Informed Engineering. I don't know if Kaveh is there or not because I only see you, but anyway, he knows that the idea of the Climate Informed Engineering is that the resolution. Oh yeah, hi, Atin is there. Oh, hi, Kaveh is there too. Okay, great to see you guys. So the resolution of the climate data they claim they can produce, I think they already did that. I should not use the word claim anymore. At the resolution of 1 kilometer by kilometer, with the time resolution of few minutes. And we believe if we utilize this type of climate data with this accuracy into our modeling, we will hopefully be able to produce more reliable predictions.
Continue.
Okay. All right. Another question came in. Manzo is asking, what other related parameters do you envisage to add to SVI in future work?
Okay, that's a very good question. That's probably the next paper we wanted to write, but let me elaborate a little bit. So there is a slide I showed here, this one. So there are other studies that they used more, as your audience is asking, our colleague is asking, they used more indicators to determine the degradation. We choose only 4 of them. And to begin with that, if you want to go in that direction, we add more parameters to quantify degradation. I would probably include compaction. I would probably include wind, for example. And there is a roadmap already. So they have like about 12, soil nutrient imbalance, pollution, for example. We use only soil erosion, salinization, SOC, and pH. But other parameters, yeah, definitely. I would have liked to include compaction, but this again, it goes back to your first question. It goes to Grace's question. is we are mathematicians. We work with data. We are all constrained by the data. If I don't have high quality, good data, I can't use that. Interestingly, sometimes there's so much data, they're flying around, but the way they are measured, they're different. So somebody measured data in Nigeria, somebody measured data in Australia. I can combine them. There is no standard procedure. So these are the things that needs to be coordinated at a more international level. And a place like a UN entities, they could actually take a major lead in this, that to standardize this type of measurement so we can include more indicators to talk about degradation, including compaction.
Okay, I'm happy my director is here. So I'm sure hashtag SDG, specified or customized SDG for soil is cooking. I hope I know my director has noted that. So hopefully the next one after SDG, UN will ensure to capture hashtag SDG for soil. But having said that, I want to do a bit of reality check here. Now, we have a tool that predicts soil degradation, especially not now, in the future. How do we break this down in terms of adaptation? At the end of the day, somebody somewhere must speak the so what of this and actually go and implement in a real-time, real specific, local point, to save soil. So in what way do you envisage we can really bring this home, for adaptation?
You are full of...
Sorry, before you start, I like, remind, we have a lot of people online.
Yeah, please.
Let them know
yes.
that they can ask questions.
Please remember to type your question or your contribution in the Q&A chat box. We have good opportunity. We still have quite some time. Please type in your question. We'll pick it from there. Thank you. So back to you, Nima. Reality check. How do we make this happen?
Yeah, so today you are full of good questions. So you're asking a multi-million-dollar questions. So I believe soil degradation is not a local problem. Soil degradation, I talk about soil erosion, right? Soil erosion. I talk about wind. That let's say that if there is salt in Spain, and in Hamburg people say, why would I care about salt? That is not South Europe. South Europe, they have a problem. I don't care about that. But if there is wind, if the salt rises, it can travel across even continent. So the dust does not apply for visa to cross the border. They don't just come. So these are yes, local problem, but global challenges, and global challenges require global cooperation. So the first thing that I can say in response to your question is that this is certainly not the job of one person. If you really want to transfer the product we have to the actual farmer, let's say in Spain, to see what is happening in Spain or in other places in the world, so it requires collaboration and multilateral collaboration. And I believe when we have this tool, and we are targeting for some, hopefully through this UNU hub, we are aiming for to write some high-level report that we can publicize it more, that we can bring it to the member states, and hopefully that can then help to devise a strategy to transfer this message to the farmers. There could be workshop. There could be further communication tool to make people aware that if you do this with the tillage of your land, and that will cause degradation, and that equates to this much of dollar. So this aspect we didn't cover. At this stage, we developed a quantitative tool capable of predicting degradation under different scenarios. But I agree there are much more to be done in terms of bringing it to the actual end users. And that entity, like the UN entities, is like the prime candidate to take a lead on this effort.
Okay, I can smell some good level of collaboration cooking up. You know, we'll talk more about that. But there's a follow-up question from Manzo. He's still asking, do you think adding more parameters would affect the overall accuracy and reliability of SVI?
That's a very good question. That's a very good question. So there are two parts here. When we say parameters, we have two types of parameters. First, you have, because here they didn't distinguish that, and that caused some problem. Parameters, some of them are indicators and some of them are drivers. When you look at this table, aridity, in my opinion, it should be a driver of the degradation. So in terms of the indicators, that 4 indicators we choose, if you add more indicators, let's say, I don't know, if compaction, for example, if you wanted to add, or acidification, obviously this intensity of degradation will be modified. And that's on purpose. We didn't call it soil degradation index. We call it soil vulnerability index. And because degradation, yeah, but what do you mean by degradation? You know, that's why we use the word vulnerability. So if you add more parameters, possibly you will get different values. But in terms of the drivers, that we have like 10, 20 the parameters in terms of nitrogen, phosphor, I don't know, climate, the stuff deriving the degradation. So the final list I showed today, like 10, 15, or I don't know, 15, 20 parameters we have, we work with much more numbers, with much more variable. Like I think at some point we were working with 40 different variable, and then we realized we basically went to a very fine-tuning practice to really highlight the most relevant drivers here. So we basically, our accuracy increases as we increase the number of the drivers, but at a certain point, we reach more or less a plateau. Of course, we can add more driver, but the accuracy of our model did not change anymore. So obviously, we are for less computational effort, less need to the data. So we stop at the position where the accuracy didn't change that much anymore. And the drivers we choose, not even a single one is just a random driver. All of them is based on consulting with literature and books and so on and so forth. This is just a beginning, so for sure we can improve it as well.
Okay, thank you very much, Kaveh.
Yes. Others, do you have questions? Yeah, Nima, wonderful presentation, and as always, and it's great to have you as the one of the founding directors of the UNU hub in Hamburg, which will be doing a lot of great work on soil. You've already been working with us on the soil health module of the aid program, and I hope the audience would have a chance to also go to the Sustainability Nexus aid program and check out the soil module and reach out to the team members if they have questions. So, your argument about the undervaluation of soil is very much very valid, right? So soil is so connected to every fight we have when it comes to the global environmental agenda. What do you think we should be doing as the academic community? I think even in academia, soil is not appreciated as much as it should be.
Yeah, I think perhaps I have to ask this question from you. So you're in a better position to answer that question. But I feel, Kaveh, we were not successful in communicating the importance of the soil to the relevant parties and community. But I look at some of other communities and how rightly, correctly, they basically highlighted the importance of whatever they're doing. I think I dare to say we failed in that. And one of my goals, I started the past few years, and that will be my motto over the next few years. I want to promote the importance of this, the importance of working on soil and benefits, because you need to show how it benefits a wide range of actors. And that's a problem. So far, when you say soil, you immediately think of farmer, but it is really beyond that. We need to marry with people in the climate community. We need to have a wedding between people in heritage. We need to work with the people from the foundation. Soil has offered to all of that. And you see, I even go to the Old Testament. I bring you quote from the Old Testament that it has been always around. But somehow, I feel that there's much less things. One of your colleagues from UNU, Flores, sent us an email that it seems they went to the UN document and the word soil, Daniel, actually, the word soil is the one that was mentioned the least among the keywords they looked into the documents of the UN, if I understood the email correctly. Something in that concept he was saying. And rather something.
You're
going. And I believe with initiatives like this soil health module, like the UNU hub, like the work we do, like the presentation I'm doing today to the UNU-INWEH, I think will help to turn the page, and we'll see how it goes. I'm optimistic. I'm a very hopeful person, so we'll see how it goes.
And I know we're at time and there are other questions, but so just before. I'd like to thank you again for your contribution. But also, I have another thought here, right? So you compare water with energy. Water is more undervalued in the policy world. People appreciate, its value when it's very scarce. But every country has water. Not every country. Now we have sun, but we can use sun. But in the past, we didn't. Many countries didn't have energy, and energy was recognized essentially fuel of the economic growth. So it was well appreciated. Water, is not appreciated as much as energy. One other thing I think about soil is, first of all, everywhere in the world we have soil. Even in those places that we think they're not appropriate for human life, we have soil. So we never think of soil as a scarce resource because we don't understand soil. And soil, it is associated with dust and being dirty, right? So lots of I think maybe wrong characterization of soil. So it is undervalued for a very good reason that we don't understand it. We don't understand its value and its function, and it's different. Even when we talk about biodiversity, when you see wildlife is appreciated, when you see something green is appreciated, when you see something brown and yet, that's something we have. We have to even remind people that, dry areas also have biodiversity. Biodiversity is not only about other things. Anyway, I think it's best to wrap up and ask the last question.
Yeah, thank you,
Carmen, for the comment.
Yeah. I guess what's actually climate change is driving, a kind of soil scarcity here, because as drought is intensifying, quality soil is reducing, so driving scarcity. But I guess you'll pick that conversation up, one more time. But I want to feature this question from Reza. It's saying, on a more general aspect of the topic, what are the most effective region-specific adaptation strategies that can mitigate the impact of soil degradation due to extreme weather events while enhancing soil resilience, carbon sequestration, and long-term agricultural productivity in vulnerable regions? It's mouthful, but what's your take on that?
Nima, can you stop sharing your screen?
Yes, that's a very good idea. Oh, that's good now?
Yes.
Yeah. So this is again, that's a multi-million-dollar question. Essentially, the question is, what is the remediation strategy? What is the so the solution is, of course, a sustainable land management, but the detail has to be discussed. There is a project that is running in Europe, AI for soil health. I'm a part of that project. In fact, part of this work has been conducted in the context of AI for soil health, and we have a work package specifically designed for sustainable land management in terms of the cropping, in terms of the fertilizer application, in terms of the machinery, compaction. So there is a wide range of sustainable practices we can train and utilize, hopefully supporting us, helping us with the resilience, essentially. We need to improve our resilience to the extreme events. It's easier to say than to do, actually, but yeah.
Yeah, you're right. Easier said than done, but we'll keep pushing. On this note, we have to call it a wrap. Really, thank you, Nima. Again, I appreciate the passion you brought into this, and hopefully, fingers crossed, we'll get to have the SDG 4 solved very soon. Thank you very much, and warm regards to everyone at the UNU Hub in Germany. Come visiting, not too long, okay? All right, take care now.